Hello everyone. In this video lecture, we are going to discuss about the chemistry of main group elements, and we have already discussed the four parts in this lecture series, and this is part 5. And this topic is included into the BSc 5th semester of the 3rd year student of the Bhubaneswar University of Science and Technology, and this lecture is lecture number 5 in this lecture series, and we have already discussed the 4 lectures in the particular topic. In the first lecture, we have discussed about the concept of multicenter bonding and the structure of borane, and in the second, third and fourth lecture, we have discussed about the hydrides of group 13, 14 and 15 elements. So in this lecture, we are going to discuss about the hydrides of the group 16 elements. So I am Dr. Kuldeep, and let's start the today's topic. The group 16 is consists of the following elements: the oxygen, sulfur, selenium, tellurium and polonium. Polonium is radioactive in the nature, so we are discussing the hydrides of only oxygen, sulfur, selenium and tellurium. The hydrides are covalent in the nature, and they are good example of the hydrogen bonding. So the effect of hydrogen bonding is seen very clear in the hydrides of the group 16 elements. For example, water. Second, the hydrides of oxygen are water and hydrogen peroxide, which are both liquid and covalent in the nature. The hydrides of the heavier element, that is sulfur, selenium, tellurium, are toxic, foul-smelling gases. The hydrogen bonding in water results in a high boiling point and a highly structured arrangement in the solid state, that is in the ice. And this is the structure of the ice, in which you can see the oxygen in the red color and the hydrogen are in the white color. The solid bond are the usual covalent bond, and the dotted bond are the hydrogen. So every oxygen is surrounded with the 4 hydrogen atoms in a tetrahedral arrangement. 2 are covalently bonded and 2 are hydrogen bonded. So the structure of this is the ordinary ice, a 3-dimensional structure network of the hydrogen bonding water molecule. So the hydrogen bonding gives a 3-dimensional structure to the water in the ice. Let's come first to the water. Water is formed by the direct interaction of the elements hydrogen and oxygen. Actually, dihydrogen and the dioxygen. If you combine the hydrogen gas with oxygen gas in the ratio of 1:2 mole, you will get the water in the liquid state. And the enthalpy of formation is negative. The reaction is exothermic, and the value is minus 286 kilojoule per mole. And this reaction is very exothermic and provides the basis for the development of hydrogen economy and hydrogen fuel cell. Hydrogen fuel cell is very useful for the space program. It providing energy continuously without producing any harmful byproducts. And water, as we know, is a polar molecule with dipole moment 1.86 away, and the structure is bent like this. And there are actually 6 valence electron in the valence electron with oxygen. 2 are used for the with hydrogen, and there are 2 lone pair here, 1 lone pair and other pair. 4, 5 and 6, and the angle is 104.5 degree. And as we know, the electron activity of oxygen is greater than the hydrogen. If we are talking about the Pauling scale, the oxygen is delta minus and delta plus, so there is a charge separation, molecule is polar, and the dipole moment is represented in Debye, is equal to 1.86 dB. Then water is the most widely used solvent. Water is most widely used solvent, not only because it is widely available, but also because its high relative permittivity, dielectric constant. The dielectric constant of water is around 80. Wide liquid range from approximately 0 to 100, and through a combination of its polar character and ability to form hydrogen bond, solvating ability. So there are very important properties of water which are making it a very useful solvent. They are the high dielectric constant, liquid range, and the ability to form the hydrogen bond. Many anhydrous and hydrated compounds dissolve in water to give the hydrated cation and anion. For example, copper sulfate, sodium chloride, potassium chloride, nickel chloride, nickel sulfate. There are so many numerous examples of the main group element salt as well as transition metal salt, which are soluble in water and give colorless or the colored salts. Some predominantly covalent compounds such as ethanol and acetic acid are soluble in water or miscible with it because of hydrogen bonded reaction with the solvent. So ethanol and acetic acid form the hydrogen bond when dissolved in water. Many other covalent compounds react with water in hydrolysis reaction. In addition to simple dissolution and hydrolysis reaction, the importance of aqueous solution chemistry can be seen in redox reaction and acid-base reaction. Water also acts as a Lewis base. As we know, water has a two lone pair. So Lewis base, what is Lewis base? Any species which is able to donate the lone pair of electron, and Lewis acid which is accept the lone pair of electron. So water acts as a Lewis base ligand in metal complexes. There are so many hydrated copper salt, there are so many hydrated nickel salt, and the deprotonate form means hydroxide ion OH minus, and particularly the oxide ion O2 minus are important ligand for stabilizing higher oxidation state. If you want to stabilize the higher oxidation state like +4, +5, then we need the ligand like hydroxide ion and oxide ion. For example, the oxoprines of early d block elements such as vanadium ion. In vanadium ion, the oxidation state of vanadium is +4. So +4 oxidation, which is a high oxidation state. If you want to stabilize the oxidation state, we need the ligand like oxide and hydroxide. Then come to the hydrogen peroxide. Hydrogen peroxide is a very pale blue viscous liquid. It has a higher boiling point than water. Water is 100 degree and it is 150 degree, and a greater density, 1.445 gram per centimeter cube at 25 degrees. Water has the density approximately around 1. It is miscible in water and usually handled in aqueous solution. So generally we are using the aqueous solution of hydrogen peroxide like 10%, 20%, 30%. Hydrogen peroxide is a good oxidizing agent, but it is unstable with respect to disproportionation. Disproportionation means the same molecule is oxidized and reduced simultaneously. If you look at this reaction, H2O2 liquid give H2O liquid and half oxygen, and the delta G for this reaction is negative 119 kilojoule per mole. So in this reaction, the hydrogen peroxide is reduced as well as oxidized. And the physical appearance at 298 Kelvin I have already discussed is colorless, very blue liquid. The melting point is 2.6 Kelvin and boiling point is 425. It decomposes at this temperature, and the dipole moment is 1.57 dB, which is less than water. So the polarity of hydrogen peroxide is less than 1. If you look at the structure, it is popularly known as open book structure. In this first diagram, you can see easily there are lone pair on each oxygen. And there is OH, and there is oxygen-oxygen bond. And this oxygen-oxygen bond distance in gas phase is 147.5 picometer. This distance is 147.5 picometer. More easy to visualize in this form. It is like an open book. The dihedral angle is 111 degree. So this is one plane and this is another plane. So the dihedral angle between these two planes is 111 degree, and the OOH angle in gas phase is 95 degree. So the gas phase structure of hydrogen peroxide, as we have already discussed, with oxygen atom having lone pair, the internal dihedral angle is 111 degree, and the angle, what is dihedral angle? The angle between the plane containing the OOH. OOH means one is this OOH and OOH. So the dihedral angle, the angle between the two is 111. This reaction, which I have already discussed, which reaction? This one. This reaction is highly exothermic reaction. This reaction is exothermic reaction. This reaction is slow, but it explosive when catalyzed by a metal surface or alkali dissolved food gas. So this reaction is not taking place very readily, but it becomes fast, speed up when catalyzed by a certain metallic surface. For this reason, hydrogen peroxide and its solution are stored in plastic bottle, and at a stabilizer is added. The reaction can be considered in terms of the reduction half reactions, like half molecule of H2O2 aqueous in presence of H plus sign. This is catalyst, and electron give water, H2 liquid, and the E half, E note is plus 1.68 volt. The plus sign indicate the reaction will go in the forward direction, and the H plus aqueous combined with the oxygen in the presence of electron and will produce the half H2O2 aqueous, and the E note value is again plus 0.7 volt. So both the reactions are feasible in the forward direction. As can be inferred from these standard potential, hydrogen peroxide is a very powerful oxidizing agent in the acidic solution. For example, if we have a cerium plus 3 salt in the aqueous solution in the acidic medium, it is oxidized into the cerium plus 4. So if you are going from cerium plus 3 to cerium plus 4, there is oxidation, and H2O2 itself is reduced to the water. If you check the oxidation state of oxygen here, and if you check the oxidation state is here, you will find that there is a reduction of the H2O2 molecule, and there is oxidation of the cerium plus 3 salt to the cerium plus 4 salt. And in the basic solution, hydrogen peroxide acts as a reducing. So H2O2 is very useful compound. It acts as oxidizing, but also as a reducing agent in the basic medium. It is oxidizing agent in the acidic medium, and it is reducing agent in the basic medium. If you are taking the cerium plus 4 salt and you are using the hydrogen peroxide in the basic medium, you will get the cerium plus 3 salt. So cerium plus 4 is getting to cerium plus 3, so it is reduced, and H2O2 is again oxidized to oxygen. Hydrogen peroxide is a slightly stronger acid than the water, which can be seen with the by the pK value. H2O2 when dissolved in water, it will give the H3O ion, aqueous, that is H plus ion, and the HO2 minus aqueous, and the pK value is 11.65. The oxidizing ability of hydrogen peroxide and the harmless nature of its byproduct leads to its many applications. So the basis of the application is the harmless nature of the hydrogen peroxide as compared to the other oxidizing agents. It is used in water treatment to oxidize pollutants, as a mild antiseptic, and as a bleach in textile, paper, and hair care industries. The environmentally friendly bleach, hydrogen peroxide is rapidly replacing chlorine and hypochlorite, sodium hypochlorite bleaches in industrial application, as it is environment friendly, producing only water and oxygen. The byproduct are only water and oxygen, so there is no harmless effect of hydrogen peroxide as compared to the other bleach. And approximately 85% of the cotton and wool is bleached with the hydrogen peroxide nowadays. And hydrogen peroxide is used to treat domestic and industrial effluent and sewage. It minimizes odor by preventing the production of hydrogen sulfide by anaerobic reaction in sewage and pumps. Other industrial uses of hydrogen peroxide are the oxidation of soybean and linseed oils to produce plasticizer and stabilizers for the plastic industry, as well as for the propellant for the torpedoes and the missile. And hydrogen peroxide is increasingly being used as a green source oxidant. Green means which producing very less amount of pollution. It can be used in aqueous solution if generated in situ. In situ means during the reaction, and the only byproduct is water. And let's come to the hydrides of the sulfur, selenium, and tellurium. As we already discussed, the extent of hydrogen bonding is much less for these hydrides than for water. All the hydrides are less. The extent of hydrogen bonding is depending upon the two factors, electron activity and size, and both are decreases as we are going down from oxygen to sulfur to selenium to tellurium. So water, which is a liquid due to hydrogen bonding, but the other are gases because the hydrogen bonding is very weak or is absent. Hydrogen sulfide is toxic. Its toxicity made more hazardous by the fact that it tends to anesthetize the olfactory nerves, making intensity of smell a dangerously inaccurate guide to concentration. Hydrogen sulfide is produced by volcanoes and by some microorganisms. It is an impurity in natural gas and must be removed before the gas is used. And hydrogen sulfide is easily generated in the laboratory, as we are doing during the qualitative analysis of the inorganic salt. It is used for the detection of the various trans metalline and other metalline in the qualitative analysis in the laboratory of the undergraduate laboratory as well as the postgraduate laboratories. It is easily prepared by using the ferrous sulfide and either hydrochloric acid or sulfuric acid, and we will get the H2S gas. And it can also be prepared by the hydrolysis of aluminum sulfide, which is easily generated by ignition of a mix of the element. Just take aluminum with sulfur. In the elemental state, you will get the aluminum sulfide. When this aluminum sulfide is treated with water, there is no need of the acid, and you will get the hydrogen sulfide gas. And there are the properties of the H2S gas. It is readily soluble in water and it is a weak acid. When you dissolve hydrogen sulfide in water, you will get the H3O+, that is H plus ion, and HS minus. The pK value is 6.89, which indicates it is a weak acid. The removal of the second proton is much difficult as compared to the first, and the pK2 value is much higher, around 40. The acidic solution of H2S are mild reducing agent and deposit elemental sulfur on stranding. In a similar way, if we want to prepare the H2SC and H2PE, what we have to do? Just treat the hydrogen gas with the selenium and you will get the H2C gas. Or by ferroselenide, on reacting with hydrogen chloride, you will get the H2SC, and also the aluminium selenide when treated with water, you will get the dihydrogen selenide, H2SC. Similarly, H2PE is prepared by using the following reaction. And let's come to the solubilities of the H2SC and H2P in water are similar to that of the H2S. The SD constant for the hydride, which are protic, increases from H2S to H2P. So acidic strength is increasing from hydrogen sulfide to hydrogen telluride. Like their sulfur analog, aqueous solution of H2SC and H2P are readily oxidized and deposit elemental selenium and tellurium on standing, just like hydrogen sulfide. H2PE is the most acidic among the three. Why? The size is increases as we go from oxygen to tellurium in the order oxygen, sulfur, selenium, tellurium. Down the group, atomic size increases, as we know it is a general trend, and bond strength decreases. So the bond with the hydrogen is decreases. Hence, H2P can release H plus ion more easily than H2S, making it more acidic. So the decrease in the bond strength from sulfur to tellurium increases the acidic strength. This trend in acidity is observed all along the periodic table, and size of the central atom is directly proportional to the acidity of the hydride. So the size of the central atom will determine the acidity of the hydride. And as we have already discussed, the acidic, covalent and reducing character increases in the order water is least and H2P in hydrogen telluride is maximum. Similarly, bond angle, dipole moment and thermal stability decreases in order. The bond angle in case of water is maximum, and in case of H2P it is invited. So in case of water, the size of the oxygen is small and the bonding electron pair in the OH bond are very close to each other and they repel to each other to maximum distance. But in case of H2PE, the size of tellurium is more, so the repulsion between the bonding pair is least, and we are getting is trend in the bond angle. Similarly, we can explain the trend in the dipole moment and the dipole stability. Thank you very much for watching the video.